So after we learn 3 kind of moments, and you may say why we are interested in determining those moments, okay? And that's finally the reason. This is the generalized version of one force acting from one point to another point, right? So this time, again, we are looking at multiple forces acting on different locations in the rigid body, okay? So we have like 10 forces acting on 10 locations, but obviously we don't like this original scenario because there are too many forces we have to memorize. What you can do is you just randomly pick another point, and we can move all these forces from different point to that point you chose, and to simplify the problem. However, it has to be equivalent to the original one. Okay? So you pick any point you like. So you say, okay, I want to pick point O. No problem. Or you say, I want to pick point A1. That's no problem either. Or you pick any point you like. Okay? So let's say we pick point O. So now our job is to move these forces to point O. So we already learned how to move one force from one point to another one. And we just do step by step. First of all, let's deal with F1. So we have a F1 force acting on point A1. Now we want to move from A1, move this force from A1 to point O we chose. But this point O, by the way, may not be the original point. Okay, so it's really up to us. We just count that point O. How are we going to do it? Well, we basically add 2 virtual forces at point O in this direction. Okay, 2 virtual forces. And then this virtual force, compared with this one, they are forming a couple. If they are forming a couple, then I'm going to erase this force, and then this force, and then I just add a couple. Then this virtual force left to be a real force. So first of all, you have F1 acting on point A, then I have F1 acting on point O. But then that's not enough. We need to add the corresponding moment due to this couple. And that's called M1. So then I just say, okay, I have M1. You may say, why is it in this direction? Why is it others? This is general. You can put in any direction you like, because finally you need to determine that moment vector, which is R cross F. Okay, I in general do not know what's the direction we're talking about, right? Okay, but this is M1 due to the couple due to this F1 and this F1. That's why you have R1 cross F1, which is M1. Okay, so then we're done for the first force, successfully moving from A1 to O. And then we leave it there. Then we need to do the next step, moving this F2 from point A2 to point O. We do the same thing. At the point O, we add 2 virtual forces in this direction. And then this force and this force form a couple. We erase this force. Instead, we write M2 as the moment due to this couple. And then this A2 left. So this A2 left. And then we move to the third force, F3 acting on A3. So how are we going to move F3 from A3 to O? We do the same thing, adding 2 virtual forces at point O in this direction parallel to here. And then this force and this force form a couple. You can call M3. And that's M3 is R3 cross F3. And then you have this force, which is called F3. Where is my F3? Here. Okay, so this one here. Okay, so you see, originally you have multiple forces acting on different locations. After we just do one by one, you will find out all forces are acting at one point. That's called point O. So you have 10 forces, for example, acting on this point O. How are we going to deal with those 10 forces? We need to go back to look at chapter 2. Chapter 2 basically talks about multiple forces acting a single particle. And what kind of result we got at that time? We got an equivalent resultant force, right? So you have multiple forces acting on this point. Then I'm going to erase all these multiple forces. Instead, I'm going to add one resultant force, which is the summation of all forces acting on this point O. And that's exactly what we did in chapter 2. Okay? So first of all, you have multiple forces acting on point O, and then I'm going to erase all these multiple forces at point O. I'm going to use the resultant force to represent the overall effect of multiple forces. So then I'm going to erase all these forces, F1, F2, F3, and so on, I'm going to add one resultant force. And the mathematical equation should be the summation of F1 plus F2 plus F3, and so on, depending on how many forces you have. And by the way, this F1 is the same with this F1. This F2 is the same with this F2. This F3 is the same with this F3. If you don't believe it, you go back to do this one by one. You'll find out I did not change F1 when I moved this F1 from A1 to O. Did I change it? Okay, this has to be 2 times F1 at this point O? No, we have the same. So that's why the resultant force is simply the summation, even from the beginning scenario, right? F1 plus F2 plus F3, which is the resultant force acting on point O you chose. However, we have multiple moments. We have multiple moments. How are we going to deal with the multiple moments? We don't want to deal with all the like 10, 20, 100 moments at this point. Instead, we're going to add all these moments together as well. So this is kind of new concept, right? In the past, chapter 2, we talk about the resultant force. This time, we talk about the corresponding resultant moment. Basically, you just need to add all these moments together, because all the moments are vectors. Definitely, you can add them together. How to add them together? That's a resultant moment. I use R on the shelter here. So we call this the resultant moment. Again, it's a summation, right? It's a summation of M1, where's M1, plus M2, plus M3. But then what is M1? M1 based on this one, R1 cross F1. So then the summation R1 cross F1 plus M2, which is a summation, which is R2 cross F2, and then plus R3 cross F3. So then you finally write in a simple way the summation Ri cross Fi, depending on how many forces you have. So after we get this one, then we are going to erase all these kind of moments. And then we just put one resultant moment at this point out. Okay, so finally, originally you have multiple forces acting on different locations in the rigid body. After you randomly pick any point you like, finally you get a different scenario having a resultant force acting at this point and a resultant moment at this point. So you may say, well, it's not a big deal. Originally you have 3 vectors. Finally you still need to deal with 2 vectors. Well, for this one, it may not be a big deal. But how about you have 100 forces acting on this in the rigid body? You still have only 2 vectors. And more importantly, this one is equivalent to this. Okay? So this is what we call system of forces. In other words, originally you have multiple forces. At the beginning you even have moment if you like. Okay? It's going to be finally reduced to a single resultant force and a single couple at any point you chose, which is equivalent. Okay, originally you have multiple vectors, finally you end up with 2 vectors. And we can easily find out the resultant force with the summation of all forces and the resultant moment with the summation of all the corresponding couples or moment, which is R cross F, and you add them together. Okay? This one just to show you, just in case you don't like point O, you want to choose another point O prime, that's the same thing. What you can do is, from here, you pick point O prime, you just move all these one at O prime, you find it within the same thing. Or, if you have a single resultant force and a single resultant moment, now you want to move this one to here. That's also no problem. What you need to do, this one, you just add 2 vertical forces in this direction. And then this and this form another couple. The other couple, add this one together, you finally get this M resultant moment at O prime. And then this is the resultant force. You move from O to O prime. So, no matter what, these 2 systems of forces are equivalent if they can be reduced to the same force couple system. Okay, so this is a very important concept because next chapter 4, in chapter 4, we're going to talk about the equilibrium conditions for rigid bodies. So, when we talk about rigid bodies, it's no longer the single particle problem. So you have to deal with the resultant force and the resultant moment. Okay, so this is the 3-dimensional case in general. You can pick any point you like, and this is the final result. For 2-dimensional problem, Of course, that's the same. For example, you have multiple forces acting in different locations. Can you move all these forces to a certain point you want to choose? No problem. You follow exactly what we had. But then another question is this back to the three-dimensional problem, right? So can you find a special point, a very special point, after you do this moving process? And then finally, at this special point, the resultant moment equal to 0. The resultant force can never equal 0 because these are the forces already given. So we just add them together. That's a fixed number. No matter what, we just add them together, this one. But when you talk about resultant moment, it's already due to the force, but also due to the distance vectors, right? So there's a possibility when you pick a special point, then the resultant moment happen to be 0. Now, if that's the case, we call the single force system because the couple equals 0. The answer is no. For three-dimensional problem, in general, the answer is no. You cannot find a point, and then when you move all the forces to that point, the resultant moment happen to be 0. There's no way you can find. But for two-dimensional problem, it's guaranteed to find one, or guaranteed to find a couple points. Okay, and that is what we are talking about. So for two-dimensional problem, originally we have multiple forces acting in different locations. Okay, then let's say we want to move all the forces to point O. This is the random force we pick, a random location we pick. Then we follow the same procedure. First of all, we add all the forces together, and then we add the moment of each couple together, and that's what we get, right? So finally, we get the resultant force R, which is F1 plus F2 plus F3. That is resultant force. We get the resultant moment. We got the resultant moment. That means R1 cross F1 plus R2 cross F2 plus R3 cross F3. And you add them together, you do the math, you finally get this one. For two-dimensional problem, this resultant force should be having I and J components only because that's two-dimensional. And then for the moment, the force is I and J, and then the R is also I and J. When you do the cross product, you either end up with 0, that means I cross I, or J cross J, that's 0, or I cross J, or J cross I. You'll finally end up with a K direction. So that's why the moment is always either counterclockwise or clockwise. In other words, it has to be in the in the third direction, Z direction. So if this is the case, in other words, if you have the resultant force having X and Y components, and then the moment has the Z components, then you can always find a special point, for example, point A. So that when you move these forces to point A directly, or when you move this resultant force, resultant moment to another point A, then you happen to have only one resultant force. And then the corresponding resultant moment is nothing. It's 0. And that is quite doable. But it is our job to determine this point A. You cannot randomly choose a point. You randomly choose a point, you do the calculation, in general, you cannot get 0 resultant moment. So you have to first assume there is a point, and then you need to determine that point. Using that equation, you add all the moment together, and that's equal to 0. From that equation, you need to determine the two components of point A. And in general, for two-dimensional problem, there's a multiple points. You can find out when you move all the force to that point, the resultant moment happen to be 0. Okay, and of course we are going to give you examples. Okay, this is in terms of concept.